let's start the final fight. And now, opponent, you have 1 minute to challenge the problem to the reporter.
So we would like to challenge problem number 9, magnetic assist.
Number 9? Okay, problem number 9 is accepted. reporter, you can present your results. You can start your presentation.
Hi everyone, I'm from Federal School and today we are talking about the question number 9, magnetic acids. And here's the public statement. Attract one or two magnets to a non-magnetic and non-conductive phase such that they attract a magnet suspended from the string. Investigate how the motion of the moving magnets depends on relating patterns. My key point is magnetic dipole interaction, a nonlinear behavior of magnetic forces. And here's the phenomenon, and you can see that there is the fixed magnet, and this is the playing magnet. And here's the two fixed magnets over there, and this is the wing magnet. And here's the phenomenon, just make you can understand my experience more clearly. And theory. Theory just talk about the magnetic force and the distance between magnets. If the distance between magnets decrease, the magnetic force will increase. And the gravitational force plus the magnetic force and the tension of the string will equal and will become the acceleration of the magnet. It just talk about the wing magnet. And the position vector of the suspended magnet can be like this. And that's the picture of the magnetic field B is generated by a fixed magnet. The magnetic force can be expressed as this. And this one we don't talk about here because the field is just back to the equilibrium, and that talk about the velocity, so we don't talk about it. And theory. I use the magnetic dipole. A magnetic dipole is a model used to describe a magnetic field generated by a magnetic object or particle. This is an ideal small similar to the absence of an electric dipole, and just make us easily to understand what I'm doing. A magnetic field distribution of the single magnet. If you want to do the two magnet system, just plus the whole field chaos experiments. And the non-linear motion of a magnet is caused by the deviation in the detail angle, which leads to chaos behavior. And I used two fixed magnets over there. And chaos experience, the figure below shows the result of the one of the trails. And here you can see it's the moment of the motion, and its image is viewed from a top-down perspective. The colored dots represent the three fixed magnets. The placement angle is slightly adjusted in each trail. Each time the placement angle is adjusted by 0.6 degrees, and the magnet is eventually attracted to the one of the fixed magnets and comes to rest. The final position is according to the table according the color of the magnet is started, just like this picture. It just finally attracts to one of the magnets. And the data is, and it will attract to one of magnets. So if it started at the green, at the orange one, I will put this one in the orange. And this is 1 to 30, and this is 31 to 191. And I tested 600 times, and every time I change 0.6 degrees. And here's the 3 fixed magnets on the plate. And if you enlarge the boundary, and it will become, if you enlarge this boundary over there, and it will be like this. This image attraction Abels diagram, and the color Abels are related to the Wanda property. The Wanda property is one of the conditions of chaotic behavior, making the event relapse to chaos. my experience 1. And just make you, this picture just make you know, just make you easily understand. Dependent variable, number of fixed magnets, and dependent variable, the effect of different numbers of fixed magnets on the amplitude decay of a suspended magnet to its equilibrium position. And experience setup, a magnet string is about 33 centimeters. Its suspended magnet is 3 centimeters from the base. And all deviations such as regular changes and we are ignored because that is so small. And experimental approaches we don't impress with the action of the magnet. Magnet procedure: prepare magnet and equipment. Magnet experiment with different numbers of the fixed magnet. Recorded and analyze the data, checking control variables, and start from the angle of 30 degrees. Set 5 seconds as a cycle, and find the longest planar of the magnet in one cycle using. And here, and the x-axis is the period, and the first one is 1 to 5 seconds, and the y-axis is the millimeter, and we are talking about the amplitude attenuation. The strength of the magnetic attract affects the time to reach equilibrium. The more fixed magnets there are, the faster equilibrium decreases. Experiment 2. Measure total magnetic field of a fixed magnet plus and equalitative the magnets. Ensure the total magnetic field of 2 fixed magnets plus and equalitative magnets. Depending value numbers of fixed magnets, and it's about 1 or 2 fixed magnets or more. Depending variables. Total magnetic force is mutual attraction. Experience that a magnet string is about 33 centimeters. It depends magnet is 3 centimeters from base. All deviations we are ignored because they're so small. We don't consider that. We don't consider that. Experimental apparatus will not interfere with the attraction of the magnet. Prepare magnet and equipment and suspending magnets in free from base and recording and analyze data, checking control variables. Start from an angle of 30 degrees. And the data here is very varied, and we have the x direction and y direction and z direction. And the picture over there, the x-axis is the number of the fixed magnets, and the y-axis is the Tesla. And the picture over here just want to talk about the magnetic field and magnitude. And the data over there just talk about the absolute value. And magnetic instrument the magnetic field generated by fixed magnet below. Compare the difference in total magnetic field strength between different numbers of fixed magnets. The more fixed magnet, the strong total magnetic field. As the number of fixed magnets increase, the movement of the suspending magnet is more influenced by the magnetic field. More fixed magnets can speed up the time it takes for the suspending magnet to return to equilibrium. The more magnets there are, the stronger the total magnetic field generated. Thank you for your listening.
All right. Now it's time for opponent to raise a question.
So can you change to the page where you show the FM is negatively correlated to the page.
Which page?
D part. Yeah, so this one, it says that the F is negatively proportional to R squared, but pay attention to the next page. next one. The picture, the page that shows the dipole equation. Yeah. So back on. So here I see the equation you are showing that you see so does it fit? So this one shows it is r squared times r squared. So is that against what your prerequisites?
You mean this one?
Yeah, this one.
This one is being the inverse of the 4 power of the magnitude of the position.
Okay. So can you turn to the chaos experiment? Back. Yeah. So the third point, you say that the color dots represent the 3 fixed magnets. What do you mean by 3 fixed magnets? Is it?
Here, 3 fixed magnets. And there is the blue one, but it's not really blue.
Yeah, but so since the pendulum is moving.
All right,
up.
time's up.
Okay.
Right, so it's time for the opponent to take the floor.
So hi everyone, I'm opponent from Team High School, and today I'll be opposing problem number 9 magnetic assist. So here's the problem statement. The main focus of the reporter is the magnetic dipole interaction and the nonlinear behavior of the magnetic forces. So here's the overview of the reporter's presentation. So in the theory part, they mentioned that the magnetic force is inversely proportional to the distance squared. And they show the equation of expressing the magnetic force. And in the experiment, they firstly do the chaos experiment, and they also investigate the amplitude and the period when changing the number of fixed magnets. And in the parameter includes the placement angle and the number of fixed magnets. And lastly, the data analysis. So they show the results of the more the fixed magnets, the stronger the magnetic field will be. And I think these are the pros and cons for the reporter. So I think they have clear observation on the phenomena, and they have abundance variables to discuss. And also they have a precise conclusion. But our suggestions is that they can discuss more on their data, and maybe they are missing some key parameters that actually affect the result of the experiment a lot. And here's the point I would like to discuss about the presentation. So in theory part, we see the dipole equation shown by the reporter, but I wonder if the equation really fits the realistic condition. And also the chaos condition they are mentioning, since they don't give a clear explanation on the reason why it is a chaos condition. And in the experiment, I would like to action about the graph they're showing in the chaos experiment, and also the measurement of several undefined parameters. So I'll be inviting the reporter to discuss with me. Okay, so first of all, can you turn to the page where you show the dipole equation? Yeah, this one. So the R stands for the position factor. Is that correct? Yes. So from your demonstration video, we can see that you stack many magnets on the pendulum, right? And the distance between the pendulum and the base is 3 centimeters.
Yes.
So from this equation, I only see one position factor, meaning that you simplify the force of magnetic field into one direction. But in fact, the magnetic field it not only affects one direction. If you want to simplify it into one direction, the distance must be way larger than the magnet.
From here, I want to talk about just for one base magnet, just the magnet at the base. So don't talk about the winning magnet.
Yeah,
Because I want to talk about is the field is bigger, the attraction is bigger.
Yeah, I mean, but this equation only shows that this equation only fits when the distance between the magnets is way larger than the magnet itself. So does that fit your experiment setup, since you only suspend the pendulum 3 centimeters away from the base?
Don't talk about the weighing magnet, just talk about base field.
Yes.
Yes, so that doesn't matter if it's 3 centimeters.
Yeah, but the force is exerted on, the magnetic force is exerted on the swinging pendulum. Is that true? So the magnetic force generated by the magnets on the base. Okay, so this is your setup, right?
Yes.
So what I mean is that the magnetic force generated by these magnets,
Yes.
The magnetic field exerted on the pendulum, causing it to be attracted, right? So in your experiment setup, I see that you control the distance between them is 3 centimeters, right?
No, I want to talk about just base and doesn't impact this. Don't have this. Just
So you're saying that the magnetic field on the front does not affect the one above?
Here I just want to talk about attraction. This field and the behind I plus the magnetic number of the base on the base, right?
Yes.
And it means the magnetic field attraction is bigger. So it doesn't. I'm not talking about the way magnets impact to that.
Yeah, but I'm saying about that. This equation doesn't. So Fn is you in your theory you say that Ma equals to Fn and Fm from the magnetic force and gravitational force. Is that right? So you say Ma. So Ma stands for this one, right?
Yes.
And Ma equals to the force of magnetic field and gravitational.
Right. And just talk about the only way magnets, so doesn't impact this. I apart that.
So you mean this equation does not include this one?
Yes.
So,
So
how come there's a magnetic force on this one?
Right. I just want to talk about the acceleration. If it is.
Yeah, I mean, sorry, you say that in this equation you only consider the swing magnets.
Yes.
And ignore the effect on the base.
Yes.
Yes. So how come there's a force? How come there's a magnetic force?
It itself. Itself, it has magnetic force.
So you're saying that the magnetic force generated by itself is affecting the motion of itself?
There is not have base magnet over here, and just talk about the wave magnet.
Okay, I get it. And so can you turn to the experiment where you change the amount of fixed magnets? The experiment. You change the parameters of fixed magnets. And so this graph. So to clarify, I want to ask, what does the period stand for?
Period is for and the moving is on neither, right? So I want to talk about the amplitude, and the period just talk about here. I said 5 seconds as a cycle. It means the period.
So you mean that a single period is 5 seconds?
Yes. 1 to 5 seconds, and the longest amplitude I put it into the chart.
Okay. So can you back up to the graph? So what does the y-axis stand for?
Millimeters.
Yeah, I mean, it stands for distance, right? Distance of.
Amplitude.
Yeah. So what's the amplitude you're saying about, like?
I can use this one. The center is over there, right? And
Yes.
and the amplitude is about this, like this. And we talk about amplitude is the length of this one.
So you mean the distance between the origin of the base and the pendulum, right?
Right.
So can you turn back to the graph? Since you show so you record the motion 5 minutes as a period, right?
Yes.
So you choose the biggest amplitude within these 5 seconds.
Yes.
And make this graph.
Yes.
But so since in 5 seconds the pendulum might experience 2 peaks, and so Okay, I just skip that. So can you turn to the chaos experiment? The result you're showing. Yeah, this one. So I want to ask what is the different colors in this graph stand for.
Here you can see there's 3 color of it, and I changed the angle to pull the magnets to it, and it will attract at the one of the magnets, right? And that magnet is orange, and I just put the first black in orange. And if I change the angle of it, if I change like 0.0001, and it will be like this. And that's just talk about the one-dot property, and because the one-dot property, so it will cause this. It will cause this picture.
Yeah. So can you explain the picture you are showing one by one? So what is the first one?
The first one is you can see the picture over there, and that's more beautiful, right? And if you enlarge the boundary, and it will be like this because of the one-dot poverty.
Yeah, I mean different colors stands for.
Different fixed magnets.
So you're saying that you have multiple fixed magnets?
I say it right here. The color dots represent the 3 fixed magnets, and
Yes.
and the data is over here.
Yes.
And this 100 times. So
Okay, I get it. So next one I want to discuss about, since you mentioned the motion of the pendulum is chaotic, right?
yes.
So can you show me how do you see, how do you find out the property of chaotic in both your theory and experiments?
Theory and experience. We just chaos is the chaos, so we don't talk about the theory, right? Even because I just changed the angle, and the theory didn't change the angle of the magnet.
Okay, so how do you define the chaos in your presentation?
Because one-dot poverty is one of the conditions of chaotic behavior, so that's making the magnetic, that making the image related to chaos.
Sorry, this is kind of hard to understand, so can you explain is using some physics phenomena you have observed to prove that it's chaotic?
I just talk about that, and the chaos is, here I want to talk about is the one-dot poverty, and one-dot poverty is one of the images that cause the chaos. And this picture just shows that the one-dot poverty. If the boundary over here is big,
Time's
we
up.
don't.
Okay, so opponent, you can summarize the discussion.
So in our discussion, we firstly talk about the dipole equation the reporter is showing, and she stated that the formula he's using only describes the motion of the pendulum itself, and she ignored the magnets on the base. But in my opinion, if there's no magnets on the base, the pendulum itself won't be affected by the magnetic field. And next we talk about the experiment the reporter has shown, and we clarify some confusions, things like the period and the way of experiment. So lastly, we talk about the chaos condition that the reporter has mentioned in his presentation. And she stated that these 3 graphs can show the chaotic, and the chaotic explanation is not in their theory. And that's all my presentation. Thanks.
All right, reviewer, to address the question.
I have a question from the reporter. Can you go to your conclusion slide?
Which is
Just for in the video. Could you clarify what you mean by the number of fixed magnets? As in, like on the base or on the pendulum?
Which one?
The first sentence. Like whenever you mentioned more fixed magnets, you mean on the base or the pendulum?
Means the on the base.
Okay. Could you elaborate a bit more on what you mean by suspended magnet is more influenced? Could you explain it? Just elaborate a bit more.
Because the test die will get bigger and it means the field magnetic magnetic field will get bigger, and that makes the.
Do you have any cases for that? Do you have any cases for that?
Right here.
Oh, okay, thank you. One of the reporter's assumptions earlier was to negate the importance of air resistance and changes in, your air resistance and changes. What do you think is the significance of this? I give this question to the reporter. You made the assumption that there was no air resistance, and there was no, you think that there's no air resistance or any changes.
If you want to talk about the angle changes to this, I make a.
Then
So you mean the air resistance?
I just want to air resistance.
Yeah, so I guess since the reporter mentioned that it is a chaos system, and I think the chaos system means that the result is highly sensitive to the initial conditions. So air resistance might be brought into significant consideration since it might affect a lot in the final results.
Okay.
Because that the experiment is simulate.
Sorry, could you repeat that?
The experiment is simulate.
That is simulation. So you say that was a simulation.
Yes.
Oh, okay. Just in clarification to the reporter, how do you track your pendulum? How do you track the pendulum?
I use tracker.
So you built it.
I built it.
What? How many camera angles did you use?
It's a million of it. Three cameras checking, and use the X direction, Y direction, and Z direction.
Thank you.
All right. Right, reviewer, you can take the floor.
will now be reviewing for magnetic assist. This is a false statement, and the reporter stated that they focus primarily on the magnetic dipole interaction and any nonlinear behaviors in the magnetic forces. The reporter explains the phenomenon by stating that the magnet experiences a magnetic force due to the magnetic field produced by the base magnets. The magnetic force, they also showed a inverse word relationship between the magnetic force and its distance, and also showed and tried to some of the forces and derived an expression for magnetic force from dipoles. And from their experiments, they focused on chaos experiments to find certain conditions for certain behaviors in the pendulum. And they showed this data in a fractal graph, and also it conducted some extra experiments to measure the magnetic field of the base magnets. I think the reporter had a clear presentation of their theories and their equations. They also had good explanations for the behaviors explained in their graphs, and also listed their assumptions. However, I think their theory was not sufficiently in-depth enough, and they did not really focus enough on the two-magnet system. They were quite unclear on which experiments were focusing on a one-magnet system and a two-magnet system, despite the problem statement quite clearly stating that a two-magnet system is needed. They also had a lack of error analysis, pretty important for a chaotic system that's sensitive to initial conditions. They also did not provide any 3D. They did provide 3D tracking, but they did not provide the theory to account for that. They did not really give analysis for critical values, which is again important for analyzing chaos systems. And their conclusions were quite vague in their definition, and they could have added a bit more visuals, had better time management, and also be a bit more clear on how much data they collected. During the discussion between the opponent and the reporter, they primarily tried to clarify some confusing theories and graphs, and they also tried to discuss how certain properties are measured, analyzed, and defined, like chaos. I think that the opponent did a good job of explaining the math errors and the mistakes that the reporter has made, and they also did a good job of pointing out the confusing elements in the presentation. However, I think they also failed to list the large points that the reporter was unclear on when did they use a one-magnet system, when they use a two-magnet system, and I think that's a huge part to address for the public statement. And they also didn't address the missing analysis for critical values, and they overall could have had a bit of better time management and focus on more egregious mistakes. First, they discussed the equation that the reporter showed. The opponent pointed out a contradiction and showed how it would only affect when the distances between magnets are relatively large. And the reporter claims that the point of that equation was just to show the forces by the base magnet, the base magnets. I agree with the opponent. I think that this is a form of contradiction by the reporter, and the reporter could have presented a better unified theory. They also discussed their data analysis and clarified the practical graphs and how chaos is analyzed. The reporter justified their analysis with the Wada property and also showed their experimental data. I think the reporter's data does exhibit chaos, but they could have found it a bit more. They could have been more clear on their analysis. And also during my questioning, I asked the opponent and their reporter on the importance of keeping track of error resistance. I agree with the opponent that it needs to be accounted for, and the reporter, I think the reporter is wrong to just say the simulation can make assumptions when it's supposed to mirror actual data.
Thank you. It's time for reporter to conclude.
Concluding remark. Upper says this one, and I say that it clearly shows in the phenomena and doesn't mention each other. And the upper says the magnetic field can be only one direction. And the report said the formula I use here is only for discussing the attraction of the magnetic field, not with the impact of the wing magnets. Upon said you ignore the force from the base, and the report said the hanging magnet has its own magnetic force and will impact motion. And upon says that's incorrect, and report said the two formula I used to talk about the attraction separately to make the explanation of the motion clear. Upon that, how do you find out chaotic behavior both in your theory and experiments? And report that in the theory we don't change the angle, and in the experiments we change a small angle, but the result varies significantly, which is chaos because it is sensitive to the internal conditions. Thank you.
Finally, it's time for the viewer to raise a question.
The question for the three groups. What's the R dependence of the force of a dipole field? R dependence of the force of a dipole field.
Magnetic dipole. What's the R dependence of magnetic force?
With a dependence.
R to the power R.
The distance R. Yes.
1 over R squared or 1 over R to the whatever power?
Whatever the power. So dipole.
Starting from
I
the
think it's 3, right?
Just read. What's your answer?
I think it was also 3.
What's
It's also
your
3.
answer?
One more time.
What's the R dependence of the force of the dipole field?
About 3 directions: X direction, Y direction.
Oh, no angular, just the R dependence.
the distance.
Oh, right. The R.
Yes.
It's the position vector.
So
The R is-
how the magnetic force or the magnetic field depends on the distance.
Okay, well, your slide you say is R squared. You see, true or not? Dipole field.
One more time.
In your slide, you say that the magnetic force is R squared, 1 over R squared. Force, so it's true.
R squared.
You show the page of R where? Oh, yeah, so this is true for now.
That just talk about the wave mechanism. And right here is talk about the fixed mechanism. Your question is talk about fixed mechanism.
So I have the same question for 3 of you that because the problem title is magnetic assist, can you tell me what kind of magnetic assist it is in this experiment? You can explain from the results or from the mechanism, depends on you. This assist, what kind of assist is provided?
I use the attraction over there, and that makes the non-linear motion. So I think the attraction assists the non-linear motion.
I was thinking more of like salty energy of the magnet. I think that the magnetic field is like active work on pendulum, and I think that energy speaks for like kinetic energy. And you can assume that as this system.
So if we put a normal pendulum without magnets attracting below, so the decay rate, which means the time until the pendulum gets stable, will be much longer if we have magnets on the base assisted.
Maybe I can ask you one question. We all have seen that from our first experiment in the faucet dripping pattern, we can control the flow rate to cause the transition from the periodic one to the chaotic one. And for this experiment, is it possible to change some parameters to see the similar transition from the periodic one to the chaotic one, starting from the reporter?
No, we can't because the conditions different. We change the things different.
So you don't think you can do an experiment to see that kind of transition? How about proponent?
So one of the important parameter is the release angle. And with higher release angle, it means that the pendulum has enough initial energy to go through the boundary of the basin of attraction multiple times. So if the release angle was way smaller, or the initial energy of the pendulum can be controlled at much lower, maybe below a critical value, the condition of chaos won't be as obvious, or it can be defined as maybe a periodic motion.
Thank you.
Also, I think that I agree that I think the release angle, or at least the position that you're releasing the pendulum from, is very important. As long I think you can develop some sort of setup that can very precisely control the exact position of the starting position of the pendulum. I think you can try to estimate or plot out where the transient phase would happen.
All right, so it's time for. Okay, so now for the reporter, 5, 6, 6, 5, and 5. Now for the opponent, eight, 7, 8, 6, and 6. Now for the reviewer, 7, 7, 7, 5, and 6. Okay, thank you everyone.